This will be a continuation of the digestive system. We are starting on page 18 of the packet, absorption in the small intestine. And before we start, if you need any other resources to help you explain anything, look up Susanna Hines' video on digestion and Crash Course's video on digestion. They're really good. All right, moving on. So absorption in the small intestine occurs. It does happen. The absorption passage digestive products from the GI tract into the blood and lymph. That's basically what it means. So it's absorbing shit into the blood and lymph so it can be taken to all the little body cells. Then you don't need the nutrients. And this happens through many factors, usually diffusion and facilitated diffusion and osmosis and active transport diffusion, okay? All of those types of diffusion are all happening with, your fats, your proteins, and your carbs, okay? Okay, the absorption of monosaccharides, all right? So this is where we're gonna get a little technical here. Nearly all carbs are absorbed as monosaccharides because they're the smallest building block. They're the easiest to, differentiate into other products that we need, and metabolize them. So they're gonna be the best building block for all of the small things. They are absorbed into blood capillaries through the villus. Like that little stick that we were mentioning beforehand. Those little folds. I have the little pits and these big protrusions. Yeah, so the villus are gonna take all of those monosaccharides and they're gonna catch them and they're gonna transport them. How are they gonna transport them? Well, you start with your glucose molecule, right? You're then going to move the glucose molecule with secondary active transport with sodium. So glucose is going to hitch a ride with the sodium ion, and it's going to hitchhike alongside it into the walls of the small intestine, and then through facilitated diffusion, it's going to go into the blood. Okay. Same with fructose, sugars. It's going to do facilitated diffusion, so it's just gonna, be pushed by its own pressure gradient into the wall of the small intestine through the villus, and then it will also go through facilitated diffusion to get to the bloodstream. All right, and that's for carbs. Now we're gonna go on to proteins, amino acids, stuff like that. So the absorption of amino acids, dipeptides, tripeptides, all the small things that come from larger proteins. So amino acids are the smallest part you can get from proteins, and they usually are so small that it can't really go anywhere. So you have your amino acid, and just like glucose, it's going to travel through the villus into the intestinal wall with active transport or secondary transport, secondary active transport with a sodium ion or a sodium particle or a molecule, wherever you want to call it. It's going to travel with sodium. So now the amino acids are, just chilling inside the intestinal wall, and then they just go by regular diffusion into a blood capillary of the villus. Okay? So nice and simple diffusion from there on out. So now we're going to dipeptides and tripeptides. Dipeptides and tripeptides use secondary active transport, not with sodium, with hydrogen this time, okay? So once they get past the villus and they are in the intestinal wall, they are also going to be using diffusion to get into a blood capillary, okay? So remember, carbs use facilitated diffusion, proteins use regular diffusion, right? And most proteins are absorbed as amino acids by active transport processes, and they go through the bloodstreams, like the blood capillaries in the villus of the duodenum and the jejunum. So that's where most of that is going to happen. In the ileum, not a lot of processing happens. It's more so propelling it and propelling it and propelling it until it's completely, worn out. All right. moving on, the absorption of lipids. Now these are a bit longer, a little bit harder, and they can be kind of confusing. So make sure you pay attention, make sure you understand the diagrams that they give you in the book and in the packet. So make sure you're reading the lecture book. But starting with fatty acids, okay? So fatty acids go through simple diffusion into the wall, all right? Which they are now like smaller monoglycerides now in the intestinal villus and in the wall, and then they go through regular simple diffusion into the bloodstream. Now when we get to longer micelles, micelles are a combination of long chain fatty acid chains and monoglycerides, and they kind of combine, right? So the micelles break apart, right? And then they separately diffuse through simple diffusion in through the villus, in through the intestinal wall, to where they are then resynthesized as triglycerides. So now you have a big triglyceride molecule in your intestinal wall. And once the triglyceride is resynthesized, a protein will then form and coat the mass. And once that protein coats that triglyceride, it is now called a chylomicron. And that chylomicron is now going to be sent to the lacteal of a villus, so the lymphatic system, instead of the cardiovascular system, okay? And that's the biggest, most important thing you could get from this, is that chylomicrons are made from triglycerides and a protective protein covering, okay? Chylomicrons are taken up by the lacteal of a villus. They enter the lymphatic system and then pass into the cardiovascular system. So they start in the lymphatic, they end in the cardiovascular. And they go to the liver and adipose tissue. So they are then stored. That's how fats are stored. So why chylomicrons? Well, chylomicrons are made of a couple things. They're like fatty acids, triglycerides, of course, cholesterol, and they are also insoluble in water and body fluids. They're combined with protein transporters called lipoproteins, which make them soluble. Let's see. It's also important to understand this picture right here. This is basically what the original picture with the micelle and the long chain fatty acids was. It's just a bit more real. Let's see. All right. It is also important to understand that bile salts, which you know emulsify fats, begin the chylomicron process by emulsifying those fat globules. So they don't start off as triglycerides, they have to be broken apart and then reformed to create triglycerides in order to make a chylomicron. Okay. Electrolyte absorption. So a compound which separates into ions when dissolved in water. That's what an electrolyte is, okay? It's a charged ion that is dissolved, that can be dissolved in water. It's soluble. These electrolytes include like calcium, sodium, chloride. All those are good examples of electrolytes. Active transport is used for electrolyte absorption. So it needs to be actively pushed in order to go and start diffusion. The absorption of vitamins. So there's a couple types of vitamins. There's fat-soluble vitamins. So like A, D, E, and K are absorbed with the lipids in micelles and are absorbed by simple diffusion. So basically these fat-soluble vitamins are taken in with lipids and then they are just pushed and diffused along with them by the process of simple diffusion, right? So there's no issue with them going anywhere. And then you have water-soluble vitamins, so like B and C, they're also absorbed by simple diffusion. And then you have vitamin B12, which is combined with intrinsic factor, which is produced by parietal cells in the stomach. And then that combo is absorbed in the ileum. So that's one of the bigger parts of the ileum. It absorbs that B12 intrinsic factor combo. Right. The absorption of water. So the diffusion process for water is called what? Osmosis, that's right. It depends on the absorption of electrolytes and nutrients. If you have a really high electrolyte water solution in your body, that's going to change your diffusion rates and your osmotic pressure, right? And the goal of the absorption of water is to maintain the osmotic balance with the blood, because if you have no water in your blood, that's a problem. Because plasma needs water. Plasma is 95% water. So if you don't have any plasma, you just have formed elements, and that's not going to work for your blood. It's not going to go anywhere. The breakdown of the fluids in your body is saliva creates 1 liter per day. This is all per day. Let's see. The ingestion of liquids, you're supposed to drink 2.3 liters of liquids per day. That is important to, keep yourself from dehydrating. Gastric juice makes up 2 liters of fluid. Pancreatic juice makes up 2 liters of fluid. Bile makes about 1 liter of fluid. And intestinal juice is also 1 liter of fluid. And then the small intestine is 8.3 liters of fluid. So there's a lot of fluid in your small intestine. And the large intestine itself makes up 0.9 liters. So the totals ingested and secreted, liquid count, is 9.3 liters. But you have some water that leaves when you excrete feces. So 0.1 liters of water leaves your body. So that leaves the total absorption of water to be 9.2 liters, right? Speaking of large intestine, that is where we're going next. So the large intestine, as we mentioned before, starts at the ileocecal sphincter, which is where the ileum and the cecum meet in a little sphincter. That's where all of the chyme that was being spiraled throughout your stomach and your small intestine goes in order to start the feces processing, startup. The large intestine includes the cecum, the rectum, and the anal canal. The large intestine is also called the colon. You can call it either way, it's interchangeable. Simple columnar epithelium with many goblet cells secrete mucus into the large intestine because you're gonna need a lot, or else you're gonna have something called constipation, and we'll get to that later. But you need a lot of liquid to be secreted into the large intestine, so it's able to be, to continue the motility of all of the nutrients you're about to push out. And then you also have the muscularis, or the muscle of the large intestine, and you have longitudinal muscles, so those long muscles called tendinae coli. And then you also have these pouches of muscles called haustra, and we're about to go into what haustra do actually. So a lot of mechanical digestion occurs in the large intestine, and it first begins when chyme passes through the ileocecal sphincter. That is where haustral churning occurs. So this is when haustra remain relaxed until the distension of chyme. So once chyme kind of stretches your haustra around, the haustra is gonna go I'm a little full. So it's just gonna push, and then it's gonna push it up into the next haustra, and that's just gonna keep happening all throughout the large intestine, right? The walls then contract and move contents to the next haustra. Yeah. Now, again, like with the esophagus and the stomach, and sometimes the small intestine, peristalsis occurs, which is a normal rhythmic contraction of the digestive tract. Remember, it's normal. You're supposed to have peristalsis, because if you didn't have peristalsis, nothing would move in your body. All right. But there's also another kind of peristalsis that's not really talked about. It's called mass peristalsis, which is a strong peristaltic wave that begins at mid-transverse colon and pushes all the colonic contents towards the rectum. So like a big bowel movement, that's basically what that is. So if you're having like a huge bowel movement at the moment, that's a mass peristalsis, all right? It's just pushing all of the extra stuff, and it happens about mid-transverse. And it occurs 3 to 4 times a day, more than I would think. Now, while mechanical digestion occurs, chemical digestion also occurs, but it's not like the small intestine or the stomach. No. Instead of enzymes, you actually have bacteria that help with chemical digestion. Vitamins are synthesized, for example, by bacterial action, all right? And that's basically all you'll have to understand. This is a microbiome, so you don't have to understand what bacteria causes that. All right. All right. So now we're getting into the absorption and feces formation in the large intestine, right? So in the large intestine, it absorbs the water, the electrolytes, sodium, mostly sodium and chloride, and vitamins. And once all of that is taken away, you're just left with this lump in your large intestine called feces. Feces is made up of water, inorganic salts, sloughed up epithelial cells, bacteria, products of bacterial decomposition, and undigested parts of food. So like the corn you didn't swallow, yeah, that's gonna be there. Water absorption is also important because this organ specifically is all about maintaining the body's water balance. So this is where most water absorption is going to occur. All right, and then it goes back to the fluids that we've ingested throughout the day. All right, yeah. So feces, what does feces do? Defecation. So you have a defecation reflex, okay? Defecation is the elimination of feces from the rectum, right? Defecation is a reflex action aided by both voluntary contractions of the diaphragm and the abdominal muscles. And it's also involuntary in infants because they can't really control their bodily functions yet. Specifically, the external anal sphincter can be voluntarily controlled to allow or postpone defecation, all right? So you can control the external one, you can't really control the internal one because the internal one sends signals to your body that you need to go to the bathroom. All right. So clinical applications, right? So I'm sure you guys have all heard of this, but diarrhea, frequent defecation, usually not fully processed. It is caused by increased motility of the intestine, right? So everything's moving way too quickly, so that causes diarrhea to happen. And it can lead to dehydration and electrolyte imbalances because remember that the large intestine mostly absorbs the water that you've had in the day. So if everything's moving too fast, it doesn't have time to properly absorb that water, so it comes out of you. And then constipation, which is infrequent or difficult defecation. And that's caused by decreased motility. Everything's way too slow in the intestines. So the feces remains in the colon for a prolonged period of time. It's just sitting there, it's not really doing anything. And that's usually because dietary fibers, which are good for a good bowel movement, aren't usually there, and they can, like things like constipation can be alleviated by increasing fluids and dietary fiber. So if you're dehydrated, you can usually have constipation, or if you're not really eating fiber, you can also have constipation. All right, so let's see. The regulation of gastric secretion and motility. Okay, so gastric secretion is regulated by both nervous and hormonal mechanisms. And then you also have stimulation that occurs in 3 overlapping phases. So overlapping meaning that they can occur at the same time, or they can occur all like at the same time. They could all be happening in this one span of time. Okay, and this all starts with the cephalic phase. Cephalic head. Remember chapter 1, cephalic head. So this phase starts in the head. It consists of reflexes by the sensory receptors in the head, and basically it's like the sight, the smell, the taste, the thought of food can start gastric secretion. And motility, pepsinogen will start to be secreted, hydrochloric acid and gastrin will start to be secreted as well, because now you're hungry, right? So after the cephalic phase, you have the gastric phase. So the gastric phase happens once food enters the stomach. So once food enters the stomach, the walls of the stomach become distended, so they start to stretch. And the pH will increase because proteins have entered the stomach and buffered some of the stomach acid, because proteins need a very low acidic concentration, or a pH, in order to start digestion. The response, the stretch receptors and chemoreceptors are activated by the distension, and another result is waves of peristalsis and the continual flow of gastric juice. So until you have completely digested all of the food in your stomach, peristalsis and more gastric juice will continue to be synthesized and make sure all of that food is turned into chyme so it can, go throughout the rest of the process of the intestines. So that's phase 2, gastric phase. Okay, and then the intestinal phase. So this is the intestinal phase and the enterogastric phase. Okay. Neural regulation happens in this phase, and it is due to the activation of receptors in the small intestine. Partially digested food triggers the enterogastric reflex and decreases gastric emptying. Okay. The hormonal contribution to the intestinal phase includes gastric inhibitory peptide, all right, secretin, which stimulates pancreatic juice, cholecytokinin, or CCK, stimulates the gallbladder, and this all ends up in inhibiting gastric secretion. So this happens upon entering the duodenum, all right, and you no longer need those acidic environments in order to digest food. So this enterogastric phase basically stops the gastric secretions from occurring, secretin being a normal one, because secretin will secrete pancreatic juice to be spilled into the duodenum, which of course increases the alkalinity of the juice, right? Cholecytokinin, which is stimulating the gallbladder, will secrete bile, which will also help in lipid digestion. And all in all, this will all inhibit gastric secretion. So that's the intestinal phase / the enterogastric phase. So basically, it's just alkalining the very acidic environments of the gastric juice that were in the duodenum. All right. We are almost done. So gastric emptying. Gastric emptying is basically when the stomach starts to empty itself, so it opens the pyloric sphincter up, out, up, out, up, out, and it's letting a few loads of the chyme in the stomach to be secreted into the duodenum. So the stimuli for gastric emptying is stomach distension, so the stretching of the stomach, partially digested proteins, alcohol, and caffeine. Alcohol and caffeine can actually decrease the contractibility of your sphincters, and it can loosen them. So it will probably happen more if you've drinking any caffeine or alcohol, because as we know, caffeine is actually a natural laxative that occurs. So that's why you have to go to the bathroom after maybe like an hour if you drink coffee. All right. So the secretion of gastrin generates nerve impulses from the parasympathetic nervous system. Remember, rest and digest, parasympathetic. And then gastrin and nerve impulses stimulate the contraction of the lower esophageal sphincter and the relaxation of the pyloric sphincter, and can increase the stomach motility. So gastrin will stop the lower esophageal sphincter from contracting so you don't vomit or nothing comes flushing up into your esophagus, because you don't want that. You could get whatever Ariel said that it caused. What happens when gastric juices flow up back into the esophagus? Is it called abscess?
No, you can get GERD, or you can get a hiatal. You can get an esophageal varices. You can get esophageal hiatus.
Yeah.
There's a bunch of things.
So you could get a lot of those. So you don't want like very acidic juices flowing back up into your esophagus. So that's why it closes. But the pyloric sphincter relaxes, which will then cause all the chyme that's just flowing in your stomach to start spitting out into the duodenum. Gastric emptying occurs. That's the third step. Most food leaves the stomach 2 to 6 hours after ingestion. Carbs are the first to go, all right? They're then followed by proteins and then fats, okay? Gastric emptying is inhibited by the anterogastric reflex. So as we know from the anterogastric reflex, it's going to increase the pH, it's going to make it more alkaline, the stomach that was pushed into the duodenum, right? So gastric emptying will stop after the anterogastric reflex occurs, or it'll happen continuously and it'll start slowing down the more the reflex is started. All right. So vomiting, when gastric, juices come up through the esophagus again and they're excreted out a different way besides your ass. There's an issue called prolonged vomiting, and it is serious because the loss of gastric juice and fluids can lead to disturbances in fluid and the acid-base balance. All right, there needs to be a balance between acid and base, because if you have a more acidic body pH, a lot of bad things can happen. Same if it is too alkaline. So that's all for vomiting, by the way. The regulation of intestinal secretion and motility. As we stated in the beginning of the chapter in part 1 of this video series, the enteric nervous system responds to the presence of chyme. Segmentation is stimulated by the stretching of the small intestine, right? Parasympathetic impulses increase the motility, sympathetic decrease the motility, right? Rest, digest, fight, flight, freeze. There's the difference, okay? That's actually it for the packet. Do you have anything that you want to add?
No.
Chill. All right.